So let me give a couple of, at least introduce myself. I'm Rick Riss. I'm an analyst at ARC. I have a background in process control, so I worked for the Foxborough Company for 20 years. I worked for a chemical plant for a few years in Niagara Falls, chlor-alkali plant. Um, at at Foxborough Company, I got into a very interesting group that basically tried to tackle all the hard to control problems, right? And we would give the new engineers problems like just go control the pH of this process, right? In an unbuffered solution where the precision is really high. So, but we also worked on all forms of reactor controls. We especially did a lot of work with distillation columns and distillation control. Every kind of reactive distillation, crude distillation, et cetera, compressor surge control. So I had a lot of experience doing that. And of course, in the process of doing that, you sometimes needed to build your own simulation just to test your complicated control system. Right? And occasionally we would use those simulations to train the operator. In fact, sometimes we would put that in front of the operator so he could train us about all the things we missed when we designed that control system that suddenly he needed to take into consideration. We would show him the graphical user interface, for example, and oftentimes they would come up with some very useful suggestions. So it was kind of an iterative process. We also had a lot of familiarity with simulations when we built large complex control systems and staged them, all right, prior to shipping them. And we needed to check every I/O point. And so you would build a checkout simulator, or in some cases. And in some cases, if you had a complete dynamic simulator, you would connect that. So at ARC, I've been with ARC for about 6 years now. I cover the market studies for operator training simulator suppliers, right? And I also have also moved from process control into control of electric grids, right? So to be part of that energy transition, I was very interested and curious about how to do that. That also reflects some of my own personal experience. I did some work on wind turbines for a German company. I was their US rep, and realized that they were much smarter than I was about wind turbines, but still, they're kind of complicated machines. But then I became a commissioner in my small town of Princeton, Massachusetts, which has a small electric grid, Princeton Municipal Light Department. We have 4 linemen and one office manager. We have no substations. We're purely a distribution system. But nevertheless, we own and operate 2 1.5 megawatt wind turbines. We're also trying to put in solar panels, a Tesla battery by offshore wind. So we're doing all of those kind of things that represent the energy transition. Anyway, we have some very distinguished speakers. Can we start with first presentation? Right? So let me just give a very brief introduction. We do have this Slido poll. It's just a very simple ranking poll, and that number here is, you can get to that poll just going slido.com if you can't read it with your QR code from that distance, 9977694. And if you put that in, we'll be able to take a look at the results. All right, and so the poll results will be like this. I think that was just probably my own random entry. Rate the importance of these operator training activities. Just drag the most, so you just select them and drag the most important one up. All right, wait a minute. Now I should have another slide here. That's it, huh? Well, let me just paraphrase what I think I would have otherwise said. There you go. So, in our operator training simulation research work, we kind of broke the simulation types into the simulation of the process, with various levels of fidelity, all right? We also, anybody that has used, anyone that's ever built mathematical models of processes, we kind of have this rule of thumb: all models are wrong, some are useful, all right? So the precision, you can get to very, very high precision. In some cases, that's justified. And a lot of the oil refineries and especially brand new process units certainly like to have a high resolution process simulation. But then there's the simulation of the control system. You know, in some cases, you could actually connect the actual control system to a simulator. So that's a very precise simulator because it is the same one. Or it could actually be different hardware with exact software running. So it's a replica control system. And then there is also the simulation of the spatial geometry of the manufacturing plant. All right. And there's some very creative ways that that's done. And in fact, we have some very interesting possibilities of how that's going to work with our esteemed panelists today.
So the contents of the presentation, what we'll be doing is just a quick introduction to what we consider digital twin. It is a term that has been thrown around quite often, and it does mean different things for different people. So we just kind of nail that down for what Anglo is all about. Then we'll get into the meat of the presentation. We'll go into the background from an Anglo-American point of view, and then we'll go into the architecture. We'll discuss the benefits of these digital twins, and then we'll just have a quick peek at what's next and what Anglo is really looking for in the future. Okay, so what is a digital twin? So a digital twin, just in broad terms, if I may read off the slide, it's just an asset that provides a virtual replica capable of simulating all important characteristics of the physical environment. Nothing new to the audience there. In the environment, designers, operators, and engineers can accurately obtain the results of an improvement through simulation. There's absolutely nothing new there. However, what I would like to add, for Anglo-American, the digital twin comprises of two things. It's a process twin and it's a device twin. Now, I will be referring to these quite often in the presentation. And we are trying to represent the various layers of the plant's control system hierarchy. And very often we are asked, is this for new plants? No, it is applicable to both greenfields and brownfields project. So we use, or our digital twin is defined from the lowest level, the actual equipment, the dynamic responses, the pipes, the tanks, the conveyors, the flow rates, the densities. On top of that, we have the instruments and devices, like the SIMO codes, the drives, the instrumentation, the actual things in the field. And on top of that, we have our virtual layers, which is typically starts with the PLC or the DCS, the SCADAs, the advanced process control, the management execution systems, or the short interval control, and all the advanced layers on top of it. All physical hardware is digitally replicated. We'll be talking about that, such as the physical PLCs becomes a virtual PLC, and the actual plant becomes a virtual plant. Our partner companies for this is Honeywell. We use Rockwell and Siemens PLCs also fairly widely. Okay, so in terms of the background and getting into the meat of the presentation, just there is a bit of repeat here, and we find it fairly useful especially when we are presenting this to our stakeholders on the plant. So what is it? What is a digital twin? It is a digital representation of the real operation, as we've said, but it entails a high fidelity process simulation, which is connected to the PLCs and the DCS via that device simulation. And then what you have, you can put an operator in front of an actual SCADA that is connected to the actual advanced layer on site. And you can immediately see the benefit and that alone will have on any simulation. So the objective is, first of all, is to have an operator training station, like I mentioned, putting operators in front of a plant that reacts, that first of all looks, it feels, it reacts as a plant. And it's got the actual control system connected to it for these operators to play with and to fail on that level. Okay, so that enables SCADA familiarization, scenario identification, In addition, you also have a simulation for optimization, which is if in its own, it speaks for itself. It's useful in debottlenecking studies and scenario testing. We've got advanced process control and what we call the plant-wide optimizer. I know in the Honeywell world that's more referred to as the DQP. We have assistance for the advanced layer through the use of inferentials, using the Honeywell design suite, model identification and optimization, running a digital twin in parallel. The PLC standardization is also something that is very close to our hearts, as it becomes extremely useful doing PLC standardization and modernization in an offline plant. And then ultimate goal is having a digital mine, and it won't be a presentation about a digital twin if we don't throw in the buzzwords such as the fourth industrial revolution, which is something we absolutely subscribe to. What is it not? And it's something we often ask. So it's nothing to do with the geological model of the plant and the feed. It's not structural, it's not mechanical, and it does not include the IT systems infrastructure. Okay, so Anglo uses an ICE or a S88 structure, which is comprised into 5 levels. Level 0 is the actual plant, mining, the logistics. Level 1 is the instruments, devices, equipment, like I mentioned. Level 2, part of level 2 is the actual PLCs, and the other part is the software, which comprises the sequences, the PID, the control, the base layer control algorithm. Level 3, which is typically at an execution of between 10 seconds to 30 minutes. That is your advanced control. We use we standardized on the Honeywell Forge software. We still call it Prophet. I believe it's moved on to Honeywell Forge. Level 4, we've got plant-wide optimization, where the Honeywell DQP we use for that layer. And then on top of that, we have a level 5, which is something we really are introducing to the plants lately. So of this entire hierarchy, you can immediately see, and it's mentioned on the left-hand side of the slide, that level 0, level 1, and level 2.1, if I may call it that, is actual physical hardware in the field. It's either pumps and pipes or drives or PLCs. Now, our job, and on top of that, it's just digital. It's all control layers. It's all in a computer. So our job, part of my job, is then to make that physical world bit a digital world. And how do we do it? We've got so just zooming into those couple of layers, we have the level 0, which is the actual plant. We use Unison USD, the Unison design platform to create a high fidelity simulation. Level 1, the devices, we use other software such as, if it's a Siemens PLC, we use Simit. If it's a Rockwell, we use Echo or Emulate 3D. And then on top of that, the first part of the level 2 is where you have the actual hardware. That is a virtual controller. The software is a direct replica, and you can immediately see, if you can have a direct replica of the HMI and the actual PLC, you can have a system where you put an operator in front of it and it reacts, and that's connected ultimately to a high fidelity simulation in the Honeywell design platform, reacting like the plant does using the actual control system. Okay, just a little bit delving into these layers. Level 0, as I said, is the our high fidelity layer of the plant, is the Honeywell Unison design. There's an interesting story at Quellaveco. It's a huge copper mine in Peru that's starting up, that's being commissioned at the moment. But during the commissioning phase, there was a bit of a really good story where we had a look at the pumping station, and we could not make this pumping station work using Unison design. And we had the experts in, we had everyone. Ultimately, it was found that the design was flawed. And it caused us to change the design. And the OEM came back to us after several heated discussions and admitted that the design was flawed. But it was a great success story for the Unison design platform that pointed out, before the plant was built, that there's a fault in the design, which would have caused us quite a lot of downtime during commissioning. Okay, not much to see. Level 1 and 2, it's a CIMIT / Echo. It's Rockwell and Siemens software connecting to the PLC. It's just some examples of how it looked like. Now let's have a look at the benefit of these systems. Obviously, one of them is just you have a dynamic simulation. You can use it for case studies, scenario studies. The one that you see on the screen, the example is where we tested a crusher section. Again, the benefit I would like to reiterate is that it is often we do even dynamic simulations. We do these simulations, but it's not connected to the control system. So our simulations, the plant don't trip because the control system is not there. It doesn't optimize similar to what it would have done. So it's just that extra layer of reality that is brought, and we could test various of blasting alterations of the mine, control alternatives. We used different configurations of the bins, different crusher settings, and ultimately we decided on a combination of the pre-mentioned strategies, and we went on to implementation based on that. The Honeywell Workforce Competency Process Training Simulator, where we can put people in front of an actual SCADA environment, and like one of my people used to say, we start throwing spanners at them, and they need to navigate through the cognates of the issues that we put in front of them. We've done a couple of these. We've done one at Quellaveco. There you can see the training station. The plant hasn't even been built yet. All the operators are very confident using their own live simulation, or beg your pardon, own live SCADA system, their HMI. They know they've had SCADA familiarization training using ultimately the plant simulation in unison design to mimic the behavior of the plant, and obviously the control system, which is another Honeywell product that we use, the advanced control system. Okay, and we also use it for scenario training, where we wanted to teach them how to start up a plant, stop a plant, change a pump, all of those things. Okay, then just lastly, I would like to, on the benefits, just quickly want to go into one of the things we found with virtual commissioning, where we virtually commissioned the plant's control system, where typically an Adminis Rio plant, one of our other plants, we received the code, the code from the vendor, which in this case was a Rockwell vendor. And typically what you'd see, this is nothing against Rockwell, is when we get the site acceptance test software, we skip a virtual commissioning and training step. We go straight into loop checking, training based on a static SCADA, and ultimately we go into wet commissioning. However, at Quellaveco, with this entire digital twin, of which Honeywell has got a couple of products featuring, we included a virtual commissioning and training. Now, so before we go to loop checking, we've already done the training on the SCADA. We've done a virtual commissioning of the software, both the PLC and the advanced layer software, and only then do we go into wet commissioning. Now, the results was quite astounding. I beg your pardon, the legend's not very eligible. The orange is the one at Minas Rio, and the green is the one is the plot for the Quellaveco solution. On the y-axis is the amount of issues that was reported with the control system. What you can see here, at the point where the acceptance testing, the program was received, the amount of issues that was registered was basically the same. However, during a period where there was a virtual commissioning at Quellaveco, but nothing at Minas Rio, the virtual commissioning added or spotted an additional 1,000 to 1,500 additional issues with the process simulation, or I beg your pardon, with the control system, as was delivered to site. So you can imagine having 1,500 issues during wet commissioning that you have to sift through. It just puts an amazing strain on the commissioning process. And obviously what we've seen now is a reduction in the commissioning time, which is something we're really proud of. Lastly, we're heading towards a digital mine where any piece of equipment, let's for instance say a pump, is connected to a simulation. It's connected to our advanced suite of software. It's connected to you can get all these information in the virtual world. Then we would like to connect it to a 3D plant, which we're busy doing, and all sorts of. We're using a document management software called Cormos. It's also another product, but that gives you the electrical drawings, the instrumentation diagrams, and all sorts of information on that while you are navigating this plant in the digital world. That's what we're doing at the moment, doing some 3D plant scanning. From the 3D plant scanning, we suck in the old PNIDs, which in some cases are hand-drawn. It's difficult in those cases, but ultimately using the 3D plants that we are taking, we are delivering online PNIDs, red line PNIDs using these 3D environments. And ultimately, we would like a completely virtual environment where you can walk around and get an exceptional amount of all the engineering information from our document database. That's just a little bit on where we're heading, and of this, the Honeywell suite of software does really come into play, where all of this is connected ultimately to a process simulation, which is driven with a high fidelity nature from the use and design environment. Thank you very much.
Good morning. Glad to be here. Today I'm going to talk a little bit about what BSF is doing to enhance their operator training program, utilizing digitalization. So first I want to talk just a little bit about BASF, give you a little bit of background. So again, I'm from Geismar, Louisiana. We have approximately 1,300 employees with about 1,000 contractors. We have 2,300 acres at our site in Geismar. About 30% of that is utilized, and we have 32 production units. Okay, so with that, BSF produces over 600 different chemicals. We're in several different segments. You can see them there, from agricultural, nutrition, surface technologies. So we're all over the different segments. So a few products that our chemicals go into, you can see them all here. Probably you used some of these this morning. A lot of personal care, soaps and lotions and things like that. So a lot of BSF chemicals are out there that a lot of people don't quite know. Also, the sports arena. BSF plays a big part in the sports arena. From the footwear to the helmets to the turf that everyone walks on, plays on, BSF Chemicals plays a big part in all of these. So a little bit about that, about BSF. So let's get into talking a little bit about our digitalization for our operator, reducing our unplanned events, increase operator discipline. So BSF has an initiative to reduce unplanned events, increase operational discipline using new tools. So when I talk to this presentation, BSF has lots of tools to train on. So when I talk digitalization, it doesn't mean that we're going away from traditional training. It's that we are kind of bolting on digitalization to some of the traditional training. So this is what we're looking at for the future and how we can move into the newer generation. So one of the things that we're looking at that we have implemented is our enhanced reality simulators. So our enhanced reality simulator is how we're achieving the goals that we're looking for moving into the future. So how do we achieve this? So with that enhanced simulation, we needed to key in on the human component. So how do we key in on the human component? So if we look at some of our root cause failure analysis, we can pull out those human components. So we can zero in whether it's equipment reliability, if it's startup shutdowns. we can see that human component and how it plays into failures, okay? And how we can bring in digitalization into our training to help that. So we want our operators to have the best tools available so they can be as successful in their job as possible. The big point of this also is we're trying to reduce that downtime incidents and maximize profitability, because in the times we're in now, with supply chain issues and needing to keep the plants running, what is the best way to train our personnel to reach that goal? All right. Okay, so let's talk a little bit about our historic approach. So our historic approach was a self-directed, utilizing our SMEs, utilizing trainers, but it relied heavily on having operators read and comprehend numerous operating procedures. So as we know from our learning pyramid that when we read something, we retain about 10% of that. So, but if we can actually do the task, simulate the task, we retain about 90% of that. So this is some of the data that, you know, is out there and we proved during our pilot. So early 2017 is when we began researching different ways to enhance our current operator training process and developing ideas for digital interactive procedures. So we went to conferences, we reached out to companies, we brought different companies in, we talked to them. So what we did when we brought Vuvio in, they were the closest ones that was what we were looking for, because what they did was take our plant, our process, our equipment, and build simulations with it. So with that, so the new workforce is coming in, and I've heard several presentations talking about the new workforce, the Generation Zs, you know, born after 1995. So, you know, the whole manufacturing community is seeing this. So what we had to do was we had to step up. We had to step our training up to be able to meet this new generation that's coming in, because they grew up, you know, they got a phone in this hand, they got an iPad in this hand, Snapchat, Instagram, YouTube. So we needed something digital so that they could interact and learn, because that's the way the new generation is learning. So when you go out and you buy something, and I've heard this a couple of times during the conference, when you go out and buy something, you never read the manual. Manual's confusing, leaves a lot of interpretation. What do? You Google it. You go to YouTube. All right, I do it all the time because it's very specific to what I want to see and do. So again, this is the same principle that we're trying to transition to in the manufacturing community. Okay, so let's talk about a little bit about some of the challenges. These aren't new challenges for the manufacturing community. I mean, these are always top priorities. EHS. I mean, what EHS enhancements do we see with bringing in digitalization? How can digitalization tie in with EHS? Equipment reliability. It's very important that our equipment runs. So how do we train our employees to where they're starting up equipment safely, shutting it down safely, so they're not damaging the equipment, and they're not in harm's way. Process safety compliance, this is big. Process safety. How do we ensure that with our training that we are ensuring that operators have the competency? And if they don't have the competency, how are we doing training remediation? So how do we remediate when they're not meeting the competency level that we need? And that's not only on refresher training, but it's also on initial training. New hire onboarding. So how can we lift our new hire onboarding with digitalization. Improve organizational transfer knowledge. This is big. This is something that a lot of companies struggle with every older employee that's leaving the workplace. How do we capture that knowledge from a 30-year, 40-year employee? How do we capture that knowledge and pass it on to the younger generation? Because somebody that's been there 30 or 40 years, something that's routine for them is not routine for a new employee coming in. So we want to use the digitalization software to capture that knowledge. And then last, standardizing across sites, shifts, whatever. We have to standardize that because you go in on one shift, say, okay, well, this is the way we're going to start up. You go in on the next shift, this is the way there's no standardization. Even though you have a procedure, everybody interprets that written procedure different. So we want to standardize using that digitalization piece. Okay, so a little on the proof of concept and our pilot. So how do we validate that this simulation, the digitalization simulation training is actually going to work? So how do we know it's viable for BASF? So BASF is big on showing the proof of concept. Is this going to actually work? Because we're not going to just jump into something that's not going to help us. It's not going to work. So we wanted to see results that would improve consistency among operators, practices contributing downtime, inefficiency, startups, shutdowns. So how did we do that? So we did that by conducting a side-by-side comparison. So we did a traditional training plan, and then we did our new digital simulation plan. So it was amazing the results that came out of that. Again, a lot of data was collected during this. So just a few things that we saw. So time to competency, 65% faster. All right. So that means an operator was able to use the digital simulator and feel confident and was able to go onto shift, take that job sooner than the traditional way of training. All right, we also saw a reduction in our subject matter experts and trainers by 73%. They did not have to spend every shift, every hour, every day with that operator. They have the digital simulator so they can actually go through and practice 24/7. Now, again, you have to remember that during training, an operator is not going to be able to put his hands on every single thing. They're not going to be able to shut down, start up. Years ago when I was training, 25 years ago, we just go out there and start shutting things down, let you start up, whatever you wanted to do. Today, it's not like that. So an operator is not able to put his hands on every single thing. So he's not as confident. So by using these simulations, it builds that confidence faster. Even though he hasn't physically did it, he has simulated it. So he understands the valving, what's going to happen. So a lot of data, but it was a great pilot. Okay, so let's talk a little bit about what we built and how we use them before we get into the demo. Hopefully my demo runs. So these are some of the modules that we built, and we'll break them down. So digital replica. So this is an actual replica of our plant to where an operator can walk around, operate, and now we've actually, the engineers use it, the supervisor uses it, we use it in onboarding, but you can walk around in a controlled environment, look at all the different pieces of equipment, walk through the whole plant, look at components. It tells you exactly what it is, where it's at. The digital procedure simulator. So in the digital procedure simulators, we have different modules. So we have a guided, we have a learn by doing, refresh, test, and the field execution module. So the first two, the guided and the learn by doing, that's more for new operators that are training. Okay, so it walks them through procedures, tells them where the valves are, it lets them interact with the equipment, start, stop pumps, open, close valves. The learn by doing is once they're more confident, understand where the equipment is, where the components are, they can maneuver around and go through the procedure and do it on their own. The guided will actually walk them in the simulation. The refresh is some of our older operators, they love the refresh. They'll take the refresh before they go to start something. They can run through it real quick, refresh their memory where the valves are, what's going to happen. And of course, the test. The test is, I've been doing a lot with the test. This is now part of our qualification process to where we actually test and look at the competencies, and they have to make a minimum test score on the simulation, on that procedure. The field execution modules, this is one that goes along with our handhelds. So we're able to take handhelds out into the field, use the field execution. So now you're taking the simulation, which is into the field. So now we can go through the procedure and then save that report as a record. It says, it'll give you the time, the person, the date. So great tool. Enhanced process views we developed. So this is basically a digital interactive process module to where we can take complicated manifolds, load racks, anything that's complicated that someone doesn't get to operate and change flows, lineups. We can utilize this to where we can put it into an X-ray mode. We can look at the flows through the pipes. We can put the valves, the valve labeling, change flows. So it gives an operator the opportunity to be able to play with these complicated manifolds prior to actually going out there and doing it. So missed lineups and things like that, we've cut out a lot of that by using these enhanced process views. A little bit on the training DCS simulation piece. We have done a few. They're not dynamic, but it gives a board operator the option to be able to go in emergency situations, and you can still play with all the controls. Again, it's not dynamic, but it gives the operator the chance to play with some of the controls in an emergency situation. All right? So we'll go to a demo. Let's see. Do I got to do anything, or does it just play? I got to hit play. Oh. Okay, there it goes. Yeah. Okay, so we're going to look at a little demo here, and we'll run through it. I'm going to talk quick as we walk through it. Okay, so this is the digital replica. This is JPEG pictures that have been stitched together that allows you to smoothly just walk through your process. So as you walk through your process, you can look at the different pieces of equipment. You can look up, you can look down, you can do a 360 look around. Also, once we get into right here, you can see the green boxes. So the green boxes, when you hover over it, it tells you exactly what it is. So then when you click on it, it'll give you a blowed up view, and then you can kind of interact with the valve. So this is where Vuvio is unique. You can actually interact with your equipment through the simulation. And again, a lot of the newer operators, I mean, this is what they're looking for. This is what they want. And then we also catalog all of our components. So if you want to see a specific component, you can search for it. You can put a generalized verbiage up there. You find it, click on it. It takes you straight to that component. So great piece there. So this is some of the enhanced views that I was talking about. So you can see the flows through the pipes. You can start the different flows. This is a more complicated manifold here. So you can see how the valves are activated. You can put labels on them. And then you can practice doing lineups. So if we're trying to get one product to one tank or whatever, we can play with these in the simulation. All right, so let's go into, so this is the procedure simulator. So if you look, that's the replica on the right. We have a map that's on the bottom. We have our procedure on the left. And then at the top, you can see there's an action checklist. So this action checklist is what we're actually going to go through. So in a procedure, you may have one step in a procedure, but it may have 5 to 10 actions. So we pull those actions out of that procedure and we put them in that action checklist. So it may say, we're going to close all bleeds on the pump. Okay, well, we're going to pull those out. We're going to say we're going to close bleed 1, bleed 2, bleed 3, and so on. But you'll notice as we go through these, you're actually going through the procedure, you're performing the action, then you'll have a knowledge snippet. Again, organizational knowledge transfer right here. So if there's something important that needs to go in here, we've done videos, we've done text, a great option to pull some of that knowledge from operators that know something about this piece of equipment. And you'll notice, since this is the guided, it's automatically going to walk that operator to the next component that we're going to have to operate. So again, teaching the operator where these components are. This is the test simulator. Again, it looks similar, except that operator has to walk around, has to know where the components are, has to know what he's doing, and you can see you're getting instant feedback here. So it said, okay, I closed the correct valve. All right, so he has to find the next step, and this one we'll show you if we could complete it incorrectly. So we'll close or open the wrong valve, and instantly he knows, okay, I made a mistake. I opened this valve, I should have opened this valve. And you'll see at the bottom, you can go back, you can review, or you can try again. The review will take you back to the guided and let you review and then take you. So this is the test report. So this is what it looks like. So again, this is a record. So each one of my operators has one of these, has a record with this on all their testing. So this is an assignment report. This is where I go in. I can make assignments to all the operators. I assign it to them, sends them an email. They go in. They take whatever assignment I've assigned. And then this is the analytics report. So you can really zero down on what your operators are doing. All right, so here you can see we got 13 operators that's made 100%. 13 operators, 100%. You can see the average score in there, 92. Then you can see there's 7 that scored 87 and 3 that didn't pass. Okay, so now you can zero in, okay, why are these 3 operators having problems? So let's go one step further. So let's look at the procedure. All right, so it looks like those 3 are having problems with step 4. All right, so what's wrong with step 4? Is it the operator? Just don't understand it? Is it the wording? Is it confusing in the field? So these are things that you can really zero in on. So you can see. So there's 2 valves right side by side. They look identical. So they've been opened in the wrong one in the test. So again, remediation. So now I can go back. I can sit down with those 3 operators, and I can say, okay, well, let's look at step 4. You're having problems here. All right? So again, a great tool, and again, remediation. This is how we're making sure that our operators are competent, okay? All right. And that was it. All right. Okay, now, let me finish up here. A couple slides left. So let's talk a little bit about why enhanced reality simulators. Well, I pretty much explained why. Time to proficiency, learn by doing, the instant feedback. And again, the influx of the new hires that's coming in with the new generation, they need the digitalization piece. And again, I want to say we're not getting away from the traditional. So we do the simulations, but again, we still have our traditional field test. So I try to convey that when I give these talks, because people are like, oh, well, you're doing simulations and you're taking the whole field piece away. No, we're not. This is a bolt-on to the field piece. So we still do walkthroughs. We still do testing in the field. So this is just another piece to bolt on for that competency piece and ensure that our operators are understanding our process, our procedures. Okay. Last slide. All right, so return on investment. So a lot of companies are big on return on investment. All right, so if we're going to invest this kind of money, where is our return? Okay, so these are just some of the pieces that we've pulled out, okay, that we've seen. Fewer unplanned events. Okay, so when we're out swapping pumps, and again, I go back to our root cause failure analysis. When we've had swapping pumps, we've damaged pumps, shut down the whole facility. So, you know, our utilities and our wastewater, that's the front and back end, very critical. So this is where we have focused our first pilot. So improve planned events. Okay, so before we shut down one of our huge cogens, we're gonna go through and refresh train. Everybody's gonna go through their refreshers on shutting down that cogen. So what we've seen when we do this, we have taken time off as far as how long it takes to shut down. Same way with startups. When you start talking about steam and power generation on startups, if you can shorten that time by a day or two, you know, you're talking $30,000, $40,000, $50,000 a day in just steam and electricity production. So again, and data that I've collected shows this. Reduced dependency on subject matter experts for training. Again, I don't have to dedicate a trainer for these new operators. They do check-ins. So they're using the simulation and we do check-ins. Fewer customer interruptions. Again, supply chain. And then again, utilities. If our utilities plant goes down, our customers are the rest of the site. So that's why it was big for our utilities plant to implement this. And then the last piece, this was big during the pandemic. So they sent us all home and only the operators were allowed at the plant. So first thing they asked me to do, okay, well, we got to make sure we can staff the plant if the operators are out with COVID. It's like, how can we do that? I said, no problem. I said, I'll put a training plan together. I'll assign everybody the simulations. They can walk through the plant. They can look at everything. So everybody trained at home. So if we had to pull staff and stick them in an operator's position, you know, with the training, the procedure training, the replicas, if OSHA was to come in and say, show me how you train them at home, not a problem. I got it right here. Here's their test. Here's their replicas. They could walk around. They could touch everything in that simulation. I said, I've tested them all. There it is. So that is the end of my presentation. I hope everyone got a little something out of that. So.
Well, thank you. Thanks. It's a great pleasure to be here. I apologize. I had a scheduling conflict and was a little late getting here, but not too bad. New scale power training. This is, I really tuned into what I heard before. There's a lot of the same stuff we're working on, same types of things, especially for in the field operations for the new scale plant design. I got to tell you, a lot of our material that we developed was sponsored and paid for by the Department of Energy, so we have to give them credit in a lot of our presentations. So that's what this slide is here. So NuScale has a small modular reactor. It's very transformational. There's a lot of things different about it than what conventional nuclear power is. And there's a lot of things that are quite the same too. It's scalable, reliable, carbon-free power, and we can meet our global decarbonization targets with that. I think there's quite a few studies you've seen where right now, if we had to quickly get to zero carbon, nuclear is being proposed as part of that solution to get us there. So one of the big challenges we had in designing a NuScale station was our flagship plant, our flagship station has 12 reactor modules. Most conventional nuclear plants might have up to 2 control rooms that are, and 2 specific reactors, 2 larger reactors that are controlled. We have up to 12. So the challenge was typically there's 3 to 4 licensed control room operators needed to be at the controls of the control room for each reactor. How are you going to do this for 12? How big is the room going to have to be? How, are you going to have 4 operators for the 12 reactor plants? And one of the things we did right out of the bat, I think NuScale was good at, is they hired a bunch of current and former operators, which I was one. I was licensed at DC Cook in Michigan. It's a 2-unit large PWR. I was there for 26 years, either in training or operations training. So that was a challenge. The NRC the Nuclear Regulatory Commission has to accept our plan for what we're going to do as far as how we're going to man the control room and how we're going to operate. So we started off very early with trying to design the control systems for the plant that required very few operator intense attention. So you'll see a lot more automations where in the previous plant that I was at, it was you go find this valve, open this valve, and find another valve in the control, open it up, and you're checking off through your paper procedure, and you go somewhere else maybe to start the pump, and you have to send somebody out locally because you don't have the flow meter in the control room, so they got to make sure the flow is good. It was very manpower intensive for a lot of the evolutions, where we started off from the beginning with our control processes. So if you wanted to do a evolution, that evolution was automated inside the module control system. Then the operator became more of the peer checker in making sure that automation was functioning correctly. And we designed the system so that you could monitor some key indicators to make sure that if I needed to stop automation, the operator could recognize and do that right away. So very advanced alarm recognition. There's alarm filtering for that. And as far as processes, we got it. Initially, we had it down to, I think, 5. When we did some of our testing, 5 control room operators for 12 units, and then we later did another test using the same success criteria after we changed some of the way the control and the control room and automations operated, and we're at 3 licensed control room operators now. So that was a very big accomplishment, and at first when I went in there, it seemed like it was incredibly busy, but instead of having some of the transformations I've seen going to digital is in the control room, you used to have an analog gauge that said, this hydraulic pressure, and it had a meter on it, it was gauged, and they actually fed the hydraulic pressure right up to the control room. And when we transferred over to digital, the operator's like, I want this big TV screen to show a picture of this big gauge so I can see the needle move. And because it was just lack of the comfort of how you're going to adapt to digital. And this was a huge transition to me. We were, at the plant I left, we were slowly changing systems over. We probably had 5 or 6 systems that major systems were converted to digital. And we became comfortable with using them and losing a lot of the things that we were familiar with as far as I could look across the room 40 feet away and see what this gauge reads. You may not necessarily always need that. So there's a lot of changes there. Our emergency operating procedures. So if we get into a situation where the plant is in emergency operating procedures, the computer actually, for the module protection system, analyzes what the emergency is and gives you the instant criteria to say you're an emergency operating procedure. It takes you to there in the electronic procedures and you can step through it. And compared to a conventional plant, it's extremely simple. We had at the plant, we had a whole rack of paper procedures just for emergency operating procedures. This is all on one screen, and there's not a procedure now in the NuScale plant for EOP that would take you more than 15 minutes to complete, to be successful. Part of that is because of the design. The design is a passively cooled, there's no actions that an operator has to take to keep the plant safe under any condition, under any accident. The plant simply shuts down, isolates its module, and it rejects its heat to a pool, and it sits there. So there's nothing the operator could do or could not do that would jeopardize that safety function. So that's makes a lot of our task a lot simpler from designing from an operation perspective. The last bullet there, we had an integrated system validation test, which is kind of what we talked about. We brought in people from all different scopes, kind of a product test our simulator and our concept of how we would human factor design this control room. We had people that were from previous nuclear plants. They had anywhere from 10 to 12 years experience in the control room. We asked them, we had three of those, they were our supervisors. So they kind of knew the whole nuclear power world from that aspect. We brought them in for about 6 months. Along with, we brought people, some college graduates right out of college, engineering graduates, students that had no real nuclear experience at all. And we brought in people that were high school graduates, and they were our control room operators. So we decided to take a very low mix. We put together a training program that took about 6 months to train everybody on the systems that we had. And then we ran them through the simulator with all the casualties, all the normal things that you'd see for plant, and then we recorded that and validated it, made changes to the design of the control room and HFE until we were comfortable that we could do that with 3 people. So a typical legacy, or the typical plants that are operating today, plant I came from, if you were going to become a control room licensed operator, you would need anywhere from 16 to 24 months in the field as a field operator, then about 18 months of off-shift training to get a license, and then once you have a license, every 5 weeks you have 40 hours of a training week that you attend to maintain proficiency in the tasks that you need to do. So our goal was to determine if that was appropriate for one. Is this appropriate for a new scale plant as simplistic as it is? If there aren't any safety related tasks or reactor safety tasks that the operator needs to do to protect the health of the public, do we need to have as robust of a program for training as a typical nuclear power plant does? So again, we are dispatching a lot of our simulator technology in universities. So we can take a simulator and it's all digital. We can bring it in. It has all the modeling of the reactor, a secondary plant, all the processes, and we show the universities how to run the simulator, and then in their nuclear technology programs, they have that asset to use, and we get a lot of feedback from it too, especially from a human factors standpoint, because you're showing it to people that have not been, in the fleet of nuclear for any time at all. So I think we have 3 simulators now in the universities. We're installing one in Idaho, University of Idaho next week. And I think that'll be number 4. There's also requests to install these same simulators in Europe and a lot of Eastern world countries. So working towards that. We are also putting together a package that for whoever would buy a new scale plant, if it made economical sense for them to contract new scale to provide the training services in a centralized location. And this is where a lot of the virtual reality and a lot of the things that we wouldn't have to be at the plant, or a student wouldn't have to be at the plant, we could do as a service. So we're working towards that. It's still up in the air whether or not it makes economic sense or not. Maybe a operating company wants to have their own training program. We're certainly willing to work with that. Our big vision is we want to make sure we can bring to market the best of the newest SMR technology available, and kind of clear away if there's maintenance issues or things like that. We try to clear that up as our engineering and technology company. Let's see, what else we got here? We would have simulator services, services for commissioning. We have a group right now that's working at the processes and procedures for startup and testing of the first plant that we're building in at Idaho National Labs on their property there. It'll be a six module plant that's scheduled to come online and make electricity in 2029 right now. So we're submitting our final design of the buildings and the station to the NRC for approval at the end of this year, and that should take about a year and a half or two to get finally approved. We'll have construction activities that are starting up in the meantime, expecting that we will be successful. Another feature that we would have is because of our proposed emergency planning zone areas, so we don't have to have a 5 or a 20-mile emergency planning zone areas where you have to show that you can provide evacuation if you had some sort of a release or an accident where you want to evacuate people. The reactors and the modules are small enough that our dose rates aren't infected anywhere outside of the 35-acre design of the plant, so we don't need any external emergency planning zones. So if you had a power plant that was kind of in a tight, heavily populated area that was maybe a fossil fuel or something that you wanted to replace it with a new scale plant, you don't have a lot of issues with working with the state to try to figure out how you're going to put a nuclear plant in this highly populated zone and still be able to safely evacuate or shelter people if that becomes necessary. All that has to be figured out ahead of time before you're decided to put a plant there. So again, we can put right on an existing coal site. It actually saves a lot of money as far as you most likely already have a switch yard there. You have access to water. You have a rail system. You have a lot of infrastructure that's already there. In our training that we're developing, if we were to, say, go in and replace a coal plant, one of the concerns was you're going to let all the people that worked at the coal plant go, and they're going to have to find other jobs because a nuclear plant job is so hard, compared to maybe some of the other technologies. So our training programs are focused around being able to parallel transfer over those current workers in there and bring them right into the new scale design. So it's not to make it any more complex than it has to be. It's a chart showing some of the direct parallel conversions that we would have in a coal plant that would transfer over to NuScale. We'd be able to take a lot of the tasks that they're already proficient at. Say they know how to do a valve lineup in the plant, or they know how to safely install, how to safely work on a piece of equipment. Those tasks would be directly transferable over into our training program, and we could minimize the gap training that we'd have to do between fossil fuels and nuclear. So, we're out to change the power that changes the world, and that's all I have. Thanks.
Before we bring questions from the audience, I'm going to do two things. One is I'm going to talk about the poll results from what you guys presented, and then I want to make sure that I direct a question that I've been taking notes on to each one of the panelists who traveled a long way here, and I want to make sure that they have a chance to participate. So first of all, in the voting, 11 people responded, pretty good out of such a small group, and by a good margin, I think the unit-specific high-fidelity process simulator was rated as the most important. Perhaps that's a consequence of suggesting that this is simulators for high-consequence units, because high-consequence units, you really want to understand that chemistry and physics. The second most important simulation was control system simulation, then spatial geometry, simulation of operating procedures, on-the-job training, classroom training, and unplanned health emergency. I kind of threw that in once because I was at a plant site doing some consulting work, and one of the things that they executed at that time was man down. All right, and so they actually put a guy up on the second deck of a distillation column, pretended he just had a heart attack, and then they had to simulate bringing in fire trucks, ambulances, and how they got that guy down. But I would say it was very useful for those abnormal situations. All right, so let me start by directing a few questions. The first question is to Abhishek, and in Chris's presentation, they made some amazingly wide-ranging collections of simulation. They simulated APC, they simulated data historians, they simulated a lot more stuff than most. And I know that one of the questions I have is, when you simulate advanced process control, like model predictive control, like DMC or something, you have to do step tests on the process. Would you actually use the models that we created, the dynamic models? Are those models accurate enough that you could actually do step testing or optimization calculations on the models that were built in this case?
So I can start by introducing myself. My name is Abhishek. I work in product management at Honeywell, Honeywell Connected Industrials specifically. And my focus is mainly around high fidelity process simulations, right? How can you use them? How can you basically take something from like the OTS simulations that you have? How do you run that against real-time data? How do you derive inferentials from it? How do you use it for optimization, APC gain updates, etc. Right? So that is my basically focus. So to answer your question, we can definitely use those high fidelity process simulations. I mean, they are already used for, let's say, like what Chris showed, like virtual commissioning, checkouts, etc. Right? So there is some amount of trust in it. There's a lot of detail into those simulations. And we can actually use that either in like a dynamic or steady state mode, right, to do various things. So one of the things that we are doing is basically using those simulations or the backbone, like the Unisim-based simulations, process simulations, to run that against real-time data and supply inferentials, right? Some kind of soft sensing measurements that are not readily available to the operators for making any decisions on like tweaking product quality or yields, right? Specifically in processes where GC measurements are not that reliable, etc. You could use actually these simulations against real-time data to kind of supply those soft sensors. For APC, we've used it for basically these simulations in like a steady state mode to kind of give gain updates, to kind of address non-linearities that, APCs typically in like highly non-linear units, APCs do a good job, right? But for highly nonlinear units, for various changes in feed, etc., you run it through a high fidelity simulation against real-time data, and you can provide those gain updates to kind of correct, the APC performance. So we've kind of used it in various forms in this way. And I think Chris also kind of hinted at some of the applications of these training simulators, right, to kind of use it for inferentials again. And I think, many other companies are also using these high fidelity process simulations to even do optimization. So they'll kind of, run external programs in Python or, basically web-based stuff, right? So basically use Python to kind of run collect data, mark data for data sets for like, okay, this is a high quality data set. It's good enough for me to kind of send it to my simulation, and then, run it against Unisim to basically generate data sets for optimization. So it's a very novel way of kind of using Unisim. So you're not kind of using it, optimizing within Unisim design, but sort of using it as a data set generation, right? Because now you have this high fidelity simulation. So a lot of work is happening around kind of leveraging some of these simulations that already exist, right? And how can we use that against real time? How can we improve operations? How can we improve, the soft sensing capabilities that typically if you don't have sensors, right, in the
Yeah,
plan.
excellent answer. I might want to retract something I said earlier. You know, I said all models are wrong, some are useful, but it really just brings to my age of my history. You know, when I started my career, our models were very trivial. The digitalization transition has resulted in more and more precise and more accurate models. And the fact that you know, we have the digital computation, we have the engineers, the tools to do this, means that suddenly we can get a lot more mileage out of these models.
Yeah, and just to actually add a note to that, right? You're not completely wrong. I mean, all models are somewhat wrong, right? But I think we figured out, okay, what are the things we can do to sort of correct these models, right? Or at least highlight the fact that, okay, you know, my model confidence or my model performance is 98%, right? So now, based on this, right now, you know, the operator can make a sort of rational decision, right, on whether to act on that soft sensing value that's coming out of my simulator or just ignore it, right? So I think.
All right, great. Now I have some questions about, you know, for Ron Lee, and I'd like Ron maybe to just give you a brief introduction of what you do for Vuvio. But when Gabriel put his presentation together, it was like YouTube for process, right? It was like, uh, uh, you know, dynamic street maps with, you know, accentuated augmented reality type of things. There was a lot of new capabilities. So what do you do for Vuvio, and and how would you characterize some of the work that Gabriel has done at BASF?
Okay, thanks. Good morning. Yeah, my name is Ronald Lee. I'm Vice President of Operations for Vuvio. Prior to that, I retired with 36 years at DuPont. Um, what Gabe showed was what we call enhanced reality to really differentiate it from the virtual reality space. And as you all know, a plant is no place to practice, okay? A plant that's running. That's not when you want people practicing. So we basically give them the real plant, okay? As it is in the field, the assets, you saw the broken valve handle. I'm a little bit embarrassed by that, but that's that real plant, okay? And so a big thing that we're seeing right now is that you can practice and learn remotely, okay? You don't have to necessarily be in the field. Also, self-paced learning. Everybody don't learn at the same pace. And I know a lot is talked about in terms of onboarding, but a big surprise, ha ha mama, is that a lot of those senior operators that you thought knew the operation really don't know it. And so what you discover is an old term we used to use called cowboying, okay? And what Gabe said is people started up differently. We find more procedures with ambiguity and people skipping steps or taking the wrong step. So when we go out with our forward engineers and take photo shots of your plant, and if you make a change, you can easily send us the photo. We can plug it into your replica and you back running. You don't have to start from scratch. So that's a paid advertisement. But anyway, we find that operator A don't do it like operator B. And there's a lot that's not in the procedures, that's not written, that they have here. And guess what happens with all of the attrition? It goes right out of the gate. And we used to call it, we lost our process. And we have all kind of analytics on the process, but it's that human asset that we fail to build. And we fail to recognize that where that human asset interacts or engages with the physical assets, that's a critical intersection. So we are all about building the human asset, giving them the most knowledge. We're in a lot of community colleges, and they love it, okay? But this is how people learn, okay? They learn different than I learned. So I don't know if I've answered your question, but that's the value of Vuvio. Knowledge transfer, knowledge capture, and allowing people to operate with the actual assets.
I think it's also important to note that as I watched Gabriel's presentation, when those senior operators failed and the junior operators passed, I'm not sure if that's the way it was, but there's a pecking order within operators. Senior, the junior operators are looking to the senior operators are saying, I'm the authority, I'm training all these
Yes.
junior operators. But as you mentioned, that it could be that maybe they need some work too. And but the fact that wherever the failures are for wherever they occurred is that because you're rating them and because you're trying to get them to pass, all of a sudden you are questioning, well, is it our training procedures that are wrong? Is it the operators that are wrong? Is there some device in the field that needs better labels or, whatever? And that's very important to update operating procedures. And operating
Yes.
procedures, they're hard to write. You need a skill set to operate, to write good operating procedures.
Yes.
All right, now I have another question for Gil. Gil is from GSES. Can you describe a little bit about you and your company and what you guys do, and how the heck did you build this simulator for NewScale? How did that come to be? Maybe DOE was involved, and what are the different uses? Obviously, it's not just operator training. You use this for NRC regulatory approval, all right? So obviously this simulator, I know for a fact that the nuclear industry has got some very sophisticated simulators, full nucleonics, reactions, meltdowns, every possible scenario you could imagine. And they also build what they call full-scale replica systems. That basically means they build an entire building with the exact replica control system, and they train operators and supervisors all at the same time in a separate a whole building dedicated. That's not done in the process industry.
Well, you know us well, so you pretty much described the company. Gil Grady, Senior Vice President of GSC in charge of business development. Background is I've been with the company almost 42 years, so I've done everything but write code. But kind of talking about, the company, we're mainly a simulation, engineering, and workforce solutions company. So here we're talking about simulation. So the NewScale was really an interesting project. They came to us, back in the early 2000s when they pretty much had a concept for the reactor vessel. If you were in yesterday's presentation, NewScale is kind of unique in its physical structure. It's got a containment structure, which is a steel tube that has a reactor and heat exchanger and everything you would normally see in a plant that kind of fills up this building. They've got in almost a single little unit. So they had that pretty well designed coming out of Oregon State, but what they didn't have was the rest of the plant. All the balance of plant, the turbines, the condensers, and everything else. So they came to us and they asked us if we could help build a simulator to help them make some design decisions. One, kind of test out the feasibility of the reactor core and its workings, but then start bolting on the rest of the plant to see how an integrated operation will be. So the plant's not designed, so typical simulator, somebody gives you a plant design and you go and you model it. In this case, there wasn't a plant design to model. So we ended up using our experience in building fossil plant simulators, smaller scale than a 1,000 megawatt nuclear plant, and kind of use that. And it was really an iterative process. So we first delivered something that was a very highly sophisticated simulation of the reactor core and the thermohydraulics associated with that, and then kind of more generic models around the balance of the plant. And they would use that to make some design decisions, sizing decisions on systems. And then we'd go through and they'd come up with a little bit more detailed design, and we'd reiterate and went through this process about 3 or 4 times until we came up with a more robust modeling of what the plant was going to look like. But then you talked about different uses of it. So that was kind of one use around the engineering design aspect and support of it. Others have talked about, the typical uses of simulation. So control room design, we talked about that yesterday and today about, how do you operate 12 reactors without 48 people, in the control room and in that conduct of operations and the information that has to be presented, so all the human factors. So it was used to support that, used to support the procedures. Again, they were trying to minimize operator interaction with the plant and automate as much as they can. That requires procedures that needed to be validated in some way other than just walking through a piece of paper. Some unique aspects, though, were, they had to present to the NRC their design. So instead of it just being a paper-based design application, they used the simulator to allow the regulators to actually visualize what was happening in the design so they could see the plant running. So they didn't have to just rely upon engineering analysis and their experience, but they could actually get on the simulator and play with it and see that it's going to behave the way the paper design says it's going to behave. And then finally, it was a marketing tool. So again, you're trying to convince people to invest in NuScale as a company to design this reactor. You're trying to convince customers to buy a radically unique nuclear design. And if you can show them this is the plant and it's working and it's going to behave the way we think it is going to produce the power we think it's going to produce, it was just a fantastic marketing tool for them. So those are kind of the major uses and value they got out of the simulator.
Well, I think that absolutely shows the power and value of simulation. I mean, mathematical models can be used for incredible things in digitalization. So now we're going to take any questions we have from the audience. Just raise your hand and either get us a microphone. Microphone will come up. And just introduce who you are.
Here with Dow. I had a question specifically with BASF and then probably the Vuvio. So really cool, like the video demo and everything. What is for like a typical plant, like the time investment in developing all of that? Because that was quite a lot that was, on there. And then my follow-up question would be, as things change, as things are, improved upon within a plant, what does that look like? Because in my mind, I'm thinking, oh my gosh, that would be a person needs like a full-time job to help keeping that updated. What does that look like? I guess I actually have one more question, but I'll let you answer those first.
Okay, so as far as time investment, our first initial pilot, we had one shift supervisor that worked with me, and Vuvio brought in 2 or 3 forward engineers. So we initially started out with right at 19 different simulations, including replica, and we did 1, 2, 3, 4 enhanced views, and that took right at 4 days. So, but again, our procedures were correct, all right? They were correct. So once we completed the photo shoot, they send it off. It comes back to us for quality review. You're looking at a couple of days quality review, and then implementation. So you're not talking a whole lot of time investment. You don't need a whole crew of people. Again, I basically had one shift supervisor that ran the whole project. We would just check in the mornings, check in the evenings. So that's as far as time investment. And then your second question was, what was your second question? Oh, yeah. So again, with all the different processes we have in all of manufacturing, you got quality, you got PSM, you got MOCs. So these were big questions when we rolled this out. It's like, all right, so there's a change on a procedure. How do we make sure the simulation gets changed? So we've actually been able to link our Vuvio simulation to our document management system. So when we have a change, and we have to change a procedure, it's linked to Vuvio. So we lock that simulation out. So they can no longer use that simulation until it's updated. So, and to tell you how quick, when you're doing an MOC, so I would be the one updating the procedure. So if it's a simulation change, I can go out. If it's a small change, I can go out, I can take the pictures, I send them to Vuvio. And I've done this, and you're looking at probably anywhere between 24 to 48 hours turnaround, and you have the new replica, the new simulation. If it's a large change, then we would have Vuvio come back out and reshoot, some of the, photos, depending on how big it is. But the ones I've done here lately, it's small changes, valve or a pump or piping or something like that. And I pretty much take the picture, send it off to them, they send it back, and it's updated. We put it back in service.
When ARC first got a demo from Vuvio, one of our discussion comments was at ARC, we've seen that there's been a lot of companies like Siemens and Aviva that have integrated their dynamic simulation, their control system simulation, and their 3D virtual simulation. And one of our suggestions to Vuvio, which they absolutely agreed with, is don't connect that, because that cost of making that connection from that 3D simulation to these other devices will kill your efficiency of economics. Does that sound correct, Ron?
Okay, and we're not trying to compete in that space. We are solely for this niche, this piece of the market, okay? And it's operator training, it's also skill maintenance training, because we're now simulating critical equipment overhauls and things. And Heather, the project duration is about 16 to 18 weeks total, okay? Thank you.
And then if I could ask a follow-up with that, so my emphasis is specifically functional safety and then SIS. And so I wanted to know, and I hear you with, it's not with the control system, but there's impairment procedures, there's those sorts of things. And so I was curious if there was anything specific, any learnings that come out of that, or anything that maybe you guys might specialize in from like a functional safety standpoint or from an SIS standpoint with that.
Yeah, when you say functional safety, you're talking about work practices or things like that, or?
No, more within the actual process itself. So the control system itself, right? A safety system would handle thing happening, but there's how do people interact with that control system?
Yeah, and the most we would do, because we're not tied in dynamically, is do some scenarios, different scenarios. What if conditions are this? What do you do? Okay, and that's based on your written procedure on how to respond to emergencies or upset conditions. Okay. Welcome.
All right, it's now 10 o'clock. On your VFairs app, if you go to auditorium and you find this session, there's a little survey about how you rate this particular session. We'd appreciate if you filled that out. Otherwise, thank you so much for coming to our session and coming to our ARC forum. It's fantastic to see so many people, and I guess my take is digitalization has definitely gotten more sophisticated. This is from somebody that started in a department called Analog System Design at Foxborough Company. All right, thank you.